everyone, and welcome to today's SANS webcast. JA3 Reasons to Rethink Your Encrypted Traffic Analysis Strategies, sponsored by Awake Security. My name is Carol Auth of the SANS Institute, and I will be moderating today's webcast. Today's featured speakers are Troy Kent, threat researcher at Awake Security, and Dave Shackelford, SANS analyst, instructor, and course author. If during the webcast you have any questions for our presenters, please enter them into the questions window located on the GoToWebinar interface at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. And with that, I'd like to hand the webcast over to Dave.
Awesome. Thanks, Carol. And hey, thanks for everybody joining us today. Me being called a speaker on this webcast is pretty loose because really this is Troy's show. And I think you guys are in for a treat because he's got some really compelling and interesting research to share with you guys. And so let's go on ahead to the next slide. And what I'd like to do is just sort of introduce the topic altogether. And I think this will be pretty obvious once I hand it over to Troy here in just 1 minute and he sort of takes off with things, because what we're finding is that the nature of the network is changing, period. Right? So I think we're seeing some technological shifts just in the industry altogether, whether that's because of things like cloud computing changing things due to software-defined networking stacks, or really also some of the protocols we've come to rely on being heavily modified and changing as we speak as well. There's a myriad number of reasons as to why the sort of approaches we've taken for network security monitoring, we're seeing some things sort of, I don't want to say change completely for the negative, but we've had, I think, almost an over-reliance on certain tactics and certain techniques that are starting to show the cracks, right? Because attackers are smart about this. They know the kind of network behavior that most organizations have within their environments. They understand the types of monitoring tools and techniques that have been put in place. I mean, the typical Fortune 500 or large enterprise environment, you can almost go down a checklist of the standard types of things that are going to be in place and used fairly heavily to try to look for malicious activity and behavior. And so one of the things we've seen happening consistently over the course of the past few years, and really this has been going on for well over a decade, but it's accelerated in recent years, is the use of encryption. And so this is a really double-edged sword that most security professionals are fairly aware of now, is the fact that, hey, look, encryption is both good and bad. It's great for protecting our data, but if the attackers are also using that encryption and we don't have some introspection to that traffic, we don't have the ability to terminate or sort of visibly see what's going on in there, then we're flying blind and we're having to make some assumptions about what that traffic might consist of, whether it's malicious, where it's going, what's included in it, you name it. There's a lot of things that I think we're all left scratching our heads and asking questions about. And of course, one of the big issues is, hey, how do we deal with this? How do we accurately detect malicious traffic and perhaps profile application behaviors when we're dealing with encryption in place within the environment? And so with that, I'm going to hand things over to Troy because I think he's got some really interesting insights into newer tools and possibly some tactics that we may be able to employ to start getting a little further ahead of this problem. So Troy, take it away.
All right, thanks a lot, Dave. I appreciate the introduction. And basically, everything that you're saying right there is essentially true in a lot of what we're going to be talking about today. So here's what's on the agenda. We have, why we want to use TLS fingerprinting in the first place, which is a good thing. Why are we having this conversation at all? We're going to talk about the current best method for TLS fingerprinting as of, before this conversation anyway, which appears to be JA3. We'll talk about why, unfortunately, JA3 is not an optimal solution for TLS fingerprinting. We'll talk about how the TLS fields are determined in the first place that make up TLS fingerprinting. So maybe we can better understand why JA3 is not optimal, and then also what we can do going forward to create a method that will be much more useful. So of course, first question, why TLS fingerprinting? Why are we having this conversation? Well, when we're talking about TLS fingerprinting, we're talking about using the data that's in the TLS traffic that is not obviously the encrypted content, since we can't see that. We want to use that information to potentially tell us what kind of application is the source of that traffic. You can think about how this would be useful in a security investigation. You may want to answer whether or not an application is a browser or whether it's not a browser. With the living off the land type attacks getting more common, you may want to tell whether or not the application, the source application, is a scripting engine or something like that. And of course, if you can't inspect the content to tell one of those things, then we have to go with what we have. We can also use TLS fingerprinting to tell us, what, if we have a fingerprint, what are uncommon applications for a device on our network, what are uncommon applications for our network in general, and maybe some uncommon destinations for an application. So if you think about it like this, if we have PowerShell traffic on our network that's encrypted, maybe all we usually see it going out to our Microsoft-owned domains, and then maybe some internal things. But then all of a sudden we see it go to a destination we've never seen before. That might be interesting to us. And of course, all of this kind of comes together to help us identify malicious or misconfigured traffic, which is of course our goal in our security operations centers. And you see the graphic on the left-hand side. Basically what I'm saying is knowing is half the battle, and when most of your traffic is encrypted, we need to know what we can use in order to still identify what these applications might be. So that's why we might want to use TLS fingerprinting. This is why we have to. So I have a bunch of articles posted in here, basically examples of different companies and groups saying that we need to move towards more encryption, or in the case of EFF, we already have by 2016, and we want to keep going in that direction. You see an example of Google saying it'll shame all websites that are unencrypted. You've probably already seen this. A couple more blog posts. There's also the proliferation of these services like Let's Encrypt, which make it very easy for you to have a valid certificate. So you can have encrypted web traffic regardless of who you are. You don't have to pay for it. The unfortunate side effect of that is if we can do it, so can attackers. And so a lot of them are using things like Let's Encrypt to encrypt their traffic. And so since we can't inspect the content of that information, we need to figure out some other way to identify when something malicious is happening. So that's what the articles are saying, that 50% by 2016, and we're still going forward. So what are we actually seeing on the networks here at Awake? So these are just 4 different networks that I looked at over the course of 24 hours. And so we're looking at encrypted traffic versus unencrypted web traffic. And we see that 77% TLS over HTTP in one example, 53% in another, 59%, and 75% in the last example. So we're definitely seeing that there's a large chunk of data that's encrypted. And so again, if we can't inspect the content, then we have to figure out some other way to help us identify when something bad is happening or something interesting. And some of you might be thinking about, what about middle boxes? Can't we just use HTTPS proxy or maybe a decryption middle box? You definitely can if you can afford it or you have the resources to do so. I did read one study, however, that showed, I think they looked at 7 different vendors of these types of middle boxes, and they found that 62% of the traffic from them had downgraded security. The reason for that is because the traffic, even if your client is all the way up to date, has the best cipher suites and everything it possibly can, the traffic between the middle box and the destination server is going to use the cipher suites and things that are supported by that middle box. So if you have the best and the greatest on your client, but your middle box does not, then it's going to be downgraded on the way out. Same thing was found, or at least similar, was found for severe vulnerabilities, or what they called severe vulnerabilities. So 58% of traffic from these middle boxes had that. And what we're talking about here is SSL, TLS vulnerabilities, freak poodle, things like that. And so you may have those vulnerabilities removed in your SSL libraries that you have installed or that are used to create applications for your hosts. But if you don't have them fixed on your middle box, then again, that outgoing traffic is going to have those vulnerabilities. And then, people talk about using HTTPS or proxies to verify certificates, or if they're not verified, to drop the traffic or to do additional inspection of that traffic. As it turns out, again, in that study, apparently it's not always the case that that's turned on by default. So that would be problem number 1. And problem number 2, again, if attackers are using things like Let's Encrypt then that is a valid certificate, and so it's not going to be invalid and won't be dropped for that reason. So if that's the case, kind of raises the question as to why we're spending money or resources on doing this. That's assuming that you can. And so now I want to talk about JA3. So assuming you're going to go the route of TLS fingerprinting, since if you don't want to use middle boxes, or if you can't use middle boxes, or if you don't trust them based off of the information on the previous slide, you can do TLS fingerprinting. And what we have as an option right now is something called JA3. So for those of you who are not aware, this is what JA3 is. Essentially, where in the left-hand side, you can see a screenshot from the JA3 GitHub. And essentially what it does is it takes some of our certain TLS fields, takes the decimal values of those fields, and it puts it together in a string, and then it will create an MD5 hash out of that string. You can see at the bottom the example of the MD5 hashes from the decimal values of certain TLS fields. The right-hand side, you see what looks like an implementation of this and an open source tool. In other words, what's happening is, so here's Wireshark, and you see down here the different TLS fields, a lot of which are used in the calculation of that JA3 hash. So it'll take all of that information and it will become this information. And so you see all of the decimal values. This is the actual output of the Python script on the JA3 GitHub. It will have all of the decimal values of the TLS fields that are being used. And on the right-hand side, you see all of the JA3 hashes. So now that we know what JA3 is, what it looks like, what's making up the JA3 hash, I want to talk about what determines those field values, what determines the extensions, what determines the extension values, the TLS versions, all of these different things. What are they actually determined by, which is then going to determine our JA3 hash. So it's important to know that there are a handful of widely used SSL libraries. For example, OpenSSL, which you might be familiar with, Boring SSL, which is used for anything that's Chromium based. So Chrome, Chromium, Opera, Electron. If you're not familiar with what Electron is, it's what Slack is based on and anything else that chooses to use Electron. And so it's important to recognize that since the TLS fields are largely determined by the SSL library used, and then also the developers using those SSL libraries, that the TLS fingerprints, regardless of whether you're using JA3 or not, are going to be very similar, if not the same, between those four different things or anything else that uses Chromium. NSS is another example of an SSL library. That's what Firefox uses. Apple Secure Transport is what Apple uses, and Secure Channel is what Windows uses. So it's important to know here that different versions add and remove different field values. So for example, if you upgrade your OpenSSL or there's some new cipher suite that comes out and that's added to an SSL library, that's going to change what the field values are. And if you think about how that hash is created, it's going to change what the hash is. Or if there's a cipher suite or some extension or value that is found to be vulnerable, then that could be removed from the next version of one of these libraries, which again is going to change those TLS field values. Another useful piece of information is that different libraries expose different field values. So in the example of Apple Secure Transport, it's notoriously not very flexible in what it allows you to access as a developer. So if you're using the Apple Secure Transport SSL library, then it's likely that your fingerprint or your TLS fingerprint is going to be very similar to other things that are using that library, which would include Safari, iTunes, anything that OS X or that is on OS X, and then anything that's developed by anyone that's also importing that library. On the flip side, Secure Channel, so what you have on a lot of Windows applications, you can change which cipher suites are used by the applications on your Windows desktop, at a network administrative level. So you could essentially change those TLS field values that we've been talking about across your entire network, which is another kind of thing to keep in mind. We're talking about fingerprinting. So based on this information, I want to tell you, what JA3 does do for us. So it does use TLS fields to attempt to identify clients, which I think is a plus and something we should focus on doing, since as Dave mentioned and as I've mentioned, if the content itself is encrypted and we can't see the content, then we want to at least use what's available to try to identify what it is that we're seeing. Another thing that it does is it creates a hash for each client that can then be shared. So the idea is that if you have some traffic, some client hellos that you take the information out of, create some JA3 hashes, say for Firefox traffic, then you can take that hash and share it with your friend at another company. And the idea is that if he sees our traffic with that JA3 hash, then what he's looking at is also Firefox traffic. So that's the idea. It's not necessarily how it works, which we'll get into later, but it does create shareable hashes. It allows you to alert yourself to when new hashes, which would presumably mean new clients, are on your network. So if you see a hash that you've never seen before, then that should be indicative of a new application being on your network that you haven't seen. Or if you see a hash on a device that you've never seen for that device, then that should be indicative of a new application. Unfortunately, that's not exactly how that works, but that is something you can keep track of and alert yourself to, so you can do additional investigation. And another thing that it does, which is important, is it excludes grease values from hash calculations. And if you're not aware, grease is something that is added in boring SSL. So anything that, chromium base, chromium, Opera, electron again. And it'll basically insert one of, I think, 10 or so different values, possible values, into different places in the TLS handshake. So you might see it in the cipher suites, you might see it in the extensions, the list of extensions, or even some of the extension values. And it's good that these are removed, because you can imagine that since it can add different grease values to different parts of the TLS client hello, then you'd end up with multiple JA3 hashes, for the same client, one after another. So it does remove that, and that's good. However, so this is straight from the JA3 GitHub as well. So we have the JA3 fingerprint for the standard Tor client. We have the JA3 fingerprint for the DriDex malware, and we have the JA3 fingerprint for Metasploit's interpreter. So the idea is that we can take these hashes, look for them on our network, and then they should be indicative of us seeing traffic from these things. Unfortunately, that's not the case. So for the first example, this saying this is the fingerprint for the Tor client. Even if it's the case that the Tor client has the same fingerprint across multiple operating systems, they're definitely going to have different fingerprints across multiple versions. When I run Tor in my own lab and on my personal computer, it has a different JA3 hash than this. And then for the example of malware, not necessarily specific to DRIDX, but just malware in general, entirely depends potentially on the victim's OS, depending on how what SSL libraries they're using and whether they're importing it at runtime or not. It also depends on the OS version of the attacker when they compiled the malware. If it's a downloader that uses Office macros, and it's going to be determined by potentially the Office version or the version, the operating system of that the malware is being downloaded to. And it will depend on whether or not the destination is a domain. And for the last example, it kind of has all of the above problems. So Metasploit's interpreter depends on what flavor of Linux you're running, what version of Linux, version of OpenSSL, and all of those things can kind of change this hash. So down at the bottom, while it says, while destination IPs, ports, and X509 certificates change, the JA3 fingerprint remains constant for the client application in these examples. Unfortunately, is not correct. And don't worry, I will show you examples of this. So the first thing that I want to show you is, here's the first 4 examples of DRIDX off of malwaretrafficanalysis.com. .net. I downloaded the PCAPs and then ran the JA3 script on them to pull out the hashes. And I only did this for the post-infection traffic, which is labeled as DRIDX malware. So in the first example, we see, if you look at the bottom left, you see that hash from the JA3 GitHub. So in the first example, we do see that hash. Then we see another hash that isn't that hash, but it's for the same application. In the second example, we don't see that hash, we see a different one. In the third example, we see the same hash as the second one, but again, it's different from the example on JA3's GitHub. And then in the fourth example, we do see that hash again from the GitHub, and then we see 3 additional hashes. So just in these 4 examples, we see what 1, 2, 3, 4, 5, 6 different possible hashes for DRIDX. So this is just one example of, one basic example anyway, of how we can get different values even for the same applications. There's some more challenges that come with JA3. So for example, if you were hoping to use the hashes generated by JA3 as kind of a way to identify specific applications, if you wanted to, for instance, import some database that's already created for a number of different applications, that's probably not how it's going to work for you. I was only able to find 2 examples of databases for these hashes. One was last updated 4 months ago, and the second was last updated 10 months ago. If you look on the right-hand side for that graphic, that's how many times the Safari browser was updated for Safari version 9, which is 8 times over the course of a year. It doesn't mean that that's the only time that the fingerprints changed, but certainly you would expect the fingerprints to change in those examples. And so something that is 4 months old or 10 months old is probably not going to be very accurate. And that's not specific to Safari. It's not specific to OS X. It certainly happens for Edge, certainly happens for Chrome, certainly happens for Secure Channel. And of course, this is just more signature-based detection, so it inherits any flaws that we've already been talking about as an industry for signature-based detection, including an entire lack of context. So what JA3 does not do that I wish it did. So it doesn't have any concept of SSL libraries or client types. In the first slide, we mentioned that we might want to identify a browser versus non-browser. We might want to identify a scripting engine. And so I can't do that. It doesn't have any concept of the SSL libraries that actually determine a lot of the fields that go into the fingerprint. And so we can't say, you can't look at a fingerprint necessarily and say, well, this is boring SSL or this is open SSL. It is a hash, which creates a number of problems. So it isn't aware of any individual values that created said hash. So we can't ask about maybe specific values that might have been in the TLS field information or the orders of those values, the lengths of those fields, things like that. We can't add or use any additional extensions. So the JA3 algorithm, if you saw that first screenshot from GitHub, included a very specific list of fields in the TLS or available TLS fields. It's also missing a lot of extensions that are available that can actually indicate unique clients, which we'll talk about more later. And it's not extensible with any newly added extensions. New TLS extensions are added probably more frequently than you think. And anytime any of those extensions has identifiable information for applications, we won't be able to use that in JA3 unless we change how JA3 works. And so how inaccurate is JA3 right now if you were to apply it to your network? And so what I found across 7 different networks is that between 34 and 42% traffic consisted of client hellos where different JA3 hashes were advertised for the same, what was actually the same application. And so basically, you have different JA3 values, which is supposed to indicate different applications, but in reality, they were actually the same application. And on the flip side of that, we had between 33 and 76% where the same JA3 hashes were advertised for what were actually different applications. And 33 is actually on the low end. It turns out that, that was one of the 7. I think the next lowest, or next highest number, or next lowest, sorry, was 69%. So it seems to be a pretty large percentage of traffic that consists of those JA3 values. I believe the reason for that is because a lot of the traffic is sourced by the same SSL libraries. So since we're not including those additional extensions and other things we can use to identify unique applications, JA3 just thinks a lot of those are the same thing when they're not. And so if you're wondering why, these are my JA3 reasons that I give for rethinking TLS fingerprinting. So there are things called conditional extensions, or what I'm calling conditional extensions. There's a number of extensions that are out there. Here's a few of them, but there's many more. SNI, for example, ALPN, padding, channel ID. You can even read in the RFCs that this is the case, but they're conditional, depending on the conditions of what's happening with the client or what's in the client's cache and some other things will determine whether or not these extensions are present for that client hello or for that handshake. And so that's obviously, since we're hashing those values in JA3, that's going to change the hash anytime the client chooses to either use or exclude any of those. The second reason would be additional extensions, as I mentioned. So some examples, signature algorithms and token binding. You can use those to help identify unique applications. I've seen cases where the only unique identifier is one of those other extensions that are not included in JA3. And so that's another reason why we're seeing JA3 say that two things are the same that are not actually the same. And new extensions. So as I mentioned, constantly new, well, maybe not constantly, but certainly more than you would think, new extensions are added to the TLS protocol, and that have identifying information or uniquely identifying information that's not being used by JA3. And just to give you an example of some of those new extensions, we have Next Protocol Negotiation 13172, which was added in 2015, Channel ID extension 30032 added in 2013, and the token binding extension, which is number 24, added in 2018. And then there's RFC 8446, which, if you're not aware, is the RFC for TLS 1.3, that if you look at the graphic above, it shows you all of the different extensions that were added in that RFC that can hold useful information for us when identifying applications. So I could just sit here talking forever about these things, and you could either choose to believe me or not believe me, but I figure it'd be best for everyone if I just go ahead and show you what I'm talking about. So what I'm going to show you is a few PCAPs. And Dave, can you tell me if you can definitely see this?
We got you, man.
All right, sounds good. Thanks. Yeah, so we have. I did this in my own lab, so I have control over which applications are doing this or not doing this, and was able to track. You know, this is definitely the same PID. This is definitely the same application, and in this case, this is Chrome. So we have 3 different client hellos, all coming from the Chrome browser, the same application. In the first example, if I click between the first client hello and the second client hello, you might notice that there is a change in the extensions that are being advertised. You may not notice which ones, but I'll go ahead and show you. So in this first example, there's no server name extension ID. There's no SNI extension. In the second example, there is an SNI extension right here. And what I found is the reason for that, at least in most common SSL libraries, is that the SNI extension is included whenever the destination is a host name, like fonts.gstatic.com, and it's excluded whenever the destination is an IP address. It's certainly possible to put whatever you want in there, but you know, using one of the most common SSL libraries, it's very likely that this is going to occur. There's also another difference here. You can see the channel ID extension is present in this first client hello, not present in the second client hello. And remember, these tiny differences are going to change the JA3 hash, since all of these values right here of the extensions that are in the client hello are going to be calculated in that hash. Then, if we look at the second and the third, we can also see that there's something different. And in this case, it is a channel ID extension again. And this is one example of some of the extensions that are cached for destination servers. That's why we see this sometimes, and sometimes we don't. It appears that if the client is already aware and it is caching this information, that the destination is not compatible with the channel ID extension, for example, then it won't send it in the client hello because it doesn't want to include that as part of the negotiation. Imagine it just saves processing and time. For the times where it doesn't know, which is probably the case for this IP address, it'll send it. Or it's also possible that it is aware that the destination server does support that extension. And we'll see a couple of examples of that kind of thing happening. But yeah, so I did show you how the different extension values are different and how that should create different hashes. But just to drive the point home, we'll go ahead and use the JA3 Python script that's offered on their GitHub on the demo, on the first demo PCAP. And we do see that there are 3 different hash values, 3 different JA3 hash values or MD5s for this traffic. And again, this is the same exact application. It's all Chrome. Go ahead and do another one just to show you that it's not specific to Chrome. Again, we're just looking at the client hellos here. That's all this means. And in the first example, again, the destination is an IP address without a host name. And the second example, the destination is the host name www.bing.com. And you can see, again, there's no server name extension in the first client hello. There is a server name extension in the second client hello. And in this example, we have a token binding extension in the first client hello that is not present in the second one. And again, token binding is very similar to channel ID. So this is another one of those cases, I believe, where the cache is coming into account. And again, they're both the same Edge browser on the same machine and within less than a second of each other. But again, we can see that there are two different JA3 values for this application. And the final example that I have is iTunes. So this is iTunes coming from OS X. We have two different domains being reached out to, three different client hellos, sorry. And you may also already notice that there's a lack of an ALPN bayou in this last one that is present in the first one to this domain. But again, we'll just show same application, it's all iTunes. In the first example, we have this extension called padding. In the second example, that extension is not there. In the first example, we have next protocol negotiation and ALPN extensions. The second example, we also have those two, but in the third example, we do not have either of those, nor do we have padding. So again, we're going to see that even though it is the same application, we have three different JA3 hashes for this activity. And this is just from the same application within the same second, going to only two different domains. And this ALPN phenomenon that we're seeing is again one of caching. It appears that since the client already is aware of whatever the server chose a second ago or less than a second ago, it doesn't need to negotiate that information again. In the case of padding, I'll go ahead and show you a piece from the RFC for padding to demonstrate this. We have in this one, the length of the record layer is 512, and the second and the third one, they're less than 256. And if you spend a lot of time in Wireshark or looking at hex or what have you, 512 may seem significant to you, and I'll show you why that is in a second. We have go ahead and play from clearance. So here we have just a snippet from the padding RFC. So you can see, if the client hello has a TLS ciphertext length between 256 and 511, since that's known to break at least one implementation of the TLS protocol, then what it can do, and you can even see it says a padding extension can be added. So that kind of plays in the whole conditional thing in order to push the length to at least 512. If you remember, that first example was exactly 512 bytes in length, and the other two were less than 256. So we saw examples in the PCAP, and we also see very clearly in the RFC that it's not always going to be added. It doesn't have to be added, but it would be added potentially in these cases where it falls between that length and for a specific reason. And so now, since I've been talking about all of these things, maybe why you can't use a middle box and just trust it out of the box, or trust that it's going to do what you think it will, or maybe you can't afford it or what have you. And why JA3, which it seems like is, until now, the most reasonable solution may not be exactly what you thought it was either. So you might be freaking out, but it's okay. I'm here to tell you to keep calm and rethink TLS fingerprints. So now I'd like to spend some time talking about, what we can do instead, what I've been doing instead, and what I find to be pretty useful. So a different approach. So what we want to do is we want to be aware of conditional extensions. So I showed you a couple of examples of those. I named a few. So we want to know what those are, what causes the conditions, so that we don't create different hashes for the same client, or don't create different fingerprints for what is actually the same application. We can use something that I'm referring to as a mapping database, which I'll explain in the next slide. We can use client TLS field behaviors in order to identify unique applications. We can use additional extension and field values that are not currently included in JA3 or new ones as they come out. We can focus on giving an answer of most confidence, which I'll explain in a bit. And we can verify data across the network and devices to make sure that what we're determining is accurate. And what I think is one of the most important things is we can move away from using a hash. So I mentioned a mapping database. So there are unique domains that are visited by specific applications that I found during my research. A lot of times this can be either upon startup or shutdown of those applications. Certainly possible that they happen, during the execution of the application itself. And it's important, we can use these domains if we see them on our network coming from a particular client with a specific TLS fingerprint to identify one of those applications. For example, if we know some domain that we've only seen Mozilla Firefox reaching out to, and then we see a new fingerprint that we're not aware of because maybe there was a version update or something like that, then that would be the first step in identifying, that it is Firefox. Of course, we wouldn't blindly just apply that every single time we saw those domains. It's always possible that somebody enters in one of those domains manually into a Chrome browser, for example. So that's why we make sure that we verify, across the network. So I mentioned client TLS field behavior. So in addition to just creating a static fingerprint out of a hash, there's actual TLS field values and orders of values, lengths, things like that, that we can use to identify or help identify applications. For example, secure transport seems to start with the cipher suite 00FF. That cipher suite can be seen in or used by other clients, other browsers, but typically it's not in the beginning, at least as far as I've seen. And I think there was a study that actually pointed that out as well. For example, Grease or extension 27, at least from what I've seen, can be used to identify boring SSL. So again, that's Chromium, Chrome, Opera, Electron, and with Slack, for example. Extension 28 seems to be specific to Firefox. Extension, or at least I guess the SSL library. Extension 21760 seems to be, or actually is a Microsoft prototype of either token binding or channel ID, I can't remember which one, but you would only see that in a Microsoft application. Browsers other than Tor, which I've seen only a few times do this, don't seem to use the heartbeat extension. So the lack of a heartbeat extension could be something on the road for us identifying whether or not something is or is not a browser. Tools like curl and wget tend to have long lists of cipher suites. I believe that's because it's using OpenSSL versus some other library that's on the operating system. Mobile clients tend to have a shorter list of cipher suites, which I think makes sense. If you imagine building your own mobile application, unless it's like a browser or something like that, you probably know which destination servers it's going to reach out to. And so if you know what those destination servers support in terms of cipher suites and extensions and things like that, then you would only have to include those. You wouldn't have to include anything else. And you could be sure that that's the type of encryption is going to be used. And there's also something that I'm referring to as proprietary or preferred libraries. So libraries that would only be used internally by a company or would at least be preferred by the company, even if it was open source. And I'll show you an example of that. So here's a Facebook application from a mobile device. In the first screenshot, we see that H2FB is in the ALPN values. We have H2, H2-FB, and HTTP 1.1. So from Googling around and looking to see what H2FB is, couldn't find any concrete information or any open source implementation of whatever that protocol is. However, based off the fact that it's a Facebook application, the server destination is a Facebook domain, and the fact that it has FB in the protocol name, it appears to be Facebook's implementation of HTTP2. And again, since it's not open source, if we do see that value or a value that ends in -FB, that might be a good indication that we're looking at something that was created by Facebook, which gives us additional context.
Hey, Troy, this is Dave.
Yep.
I just have a quick question for you.
Sure.
And I was sort of thinking about it as you were talking about, sort of these variations in different protocols and cipher suites and stuff. I mean, a lot of folks are sort of concerned about the shift towards TLS version 1.3.
Yeah.
And I think there's a lot of reasons for that. I mean, would that break some of this? Would that change what you're describing here in terms of this method? Would that have any material impact on it? Or maybe talk about that a little bit, just since that does seem to be coming pretty fast for a lot of folks.
Yeah, for sure. So you can see a little bit of TLS 1.3 on this slide, actually. And so it's pretty relevant to Fizz and Facebook and things like that. So with TLS 1.3, what I've found is that, because I actually was worried myself, if that was going to cause any issues with this kind of identification, which obviously would be a pretty big bummer. But as it turns out, all of the field values or extension values, TLS field values that are present in 1.2 and lower appear to also be present in 1.3. So I think, people have talked about some of the concern with 1.3 with respect to HTTPS proxies, for example, since the certificate will be encrypted. I also heard somebody say something about encrypted handshake. However, that's not specific to 1.3. And that also, it will encrypt the handshake, but it's later down the line than the initial client hello. I've also seen some talk about using DNS to exchange this, or to negotiate which cipher suites to use and things like that. So you don't have to have that in the initial client hello. However, I mean, it's certainly something to look out for, but if that does happen, I imagine we'd be able to apply the same kind of stuff we're doing here to whatever's happening over DNS at that point. But yeah, I mean, I can actually show you, let's do that. Let me show you what I have on TLS 1.3 real fast. So I created this for an internal presentation, but yeah, so we've all talked about TLS 1.3. But here we have an example of it. So as I was saying, the extension values that I've been talking about in the presentation so far are here: channel ID, ALPN, server name extension, all of these are here. If we look at the next slide, they're all unencrypted. So nothing is hiding the information and causing it so we can't use it. We see that type 27 that I mentioned being used by Boring SSL, and of course this is Chrome. We see the grease values, so it looks very similar. And it's actually even more similar than I would have initially thought. The way that TLS 1.3 is handled is not through these versions, is not through where you would expect to see which version is chosen, but it's actually handled in the supported versions extension. And you can see there's actually a grease value injected in here. You can see 1.3, 1.1, 1.0. And then in the server hello, the supported versions extension again. And you can see it responds, the server responds with 1.3 as its supported version, even though right here it says 1.2 very clearly. This is actually 1.3. And the reason why they implemented it that way was to get around the problems that they were seeing with the middle boxes basically not being compatible with the newer versions. So now it just kind of pretends that it's 1.2 and it should forward on that information and continue the communication with 1.3. Of course, it doesn't change the fact that it has the encrypted certificates, which is something that we'll just have to deal with. But yeah, so less so than you would think, I guess, or at least less so than I thought.
Got it.
Thanks, Dave. So we have here actually another example of 1.3. We also have this value down here, FB1A. So this is an example of another preferred or proprietary library that we can kind of identify if we can look at the field values here. I searched around for this and found this this library, open source library called Fizz, which is an implementation of TLS 1.3. It's the TLS 1.3 library developed by Facebook. Here's some code on the right-hand side of or from this project, and you can see here we have TLS 1.0 through 1.3 as potential protocol versions. We have these versions that start with 7F, which if you look it up, what that means is if it starts with 7F, then that's a draft of 1.3. So TLS 1.3 draft 20 would be 7F14. And then if you see this extra FB, and then the first byte is FB, that is actually Facebook's implementation, or Fizz's implementation anyway, of that draft of TLS 1.3. So in the example down here that we see FB1A, that's Facebook's implementation of TLS 1.3 draft 26. So this is important information that if we're not hashing it, if we're recording this information, if we're able to query on this information, then we can use this to identify at least in the first case, if no one else uses H2FB, then we can identify that Facebook developed the app, barring some very rare, weird thing, especially if we're looking at what the server responds with and what protocol is actually chosen. I suppose it's possible you can just say you support H2FB and not support it. And then in the case of FB1A, of course, that gives us the additional context that the Fizz library was used. And so that gives us a shorter list of applications that could possibly have generated this traffic, very likely something created by Facebook, but at least we can know that Fizz was involved, at least at this point. So I talked about using additional field values. So there are additional extension values that can differentiate unique applications. ALPN is one of them. I did show you an example where it was to the same domain from the same application. ALPN value was there in one, was not there in the other one. However, in the case where the ALPN value is present and different, then that can be used to differentiate unique applications. Signature hash algorithms is another one, token binding, the handshake version and the record version rather than just one of them. And the supported versions extension, especially now with TLS 1.3 and their drafts being implemented by different clients, you can use whatever is listed there to help you identify unique applications. And I mentioned focusing on the answer of most confidence. So if we know what SSL library is used, but we don't know anything else, for example, we see Greece, so we know that boring SSL is a library that's being used, but we weren't able to match it using any other rules, then we can just report what SSL library is used. It still adds additional context to the investigation. It still gives us an idea of a list of applications that could be involved in the traffic, which is much better than either calling it one thing and being wrong, or calling it nothing at all. If we know that it is or it isn't a browser, but we don't know which one, so I mentioned Heartbeat extension doesn't seem to be there for browsers or present in browser traffic. And so if we do see that, then maybe we can if we see other indications that it's not a browser are enough, we can say, okay, this isn't a browser. Or if we see, again, that it's boring SSL and we know that it's not Slack or something built with Electron, but we don't know whether it's Chrome, Chromium, Opera, or even, actually I saw an article today that said that Microsoft was building their own browser based on Chromium. Maybe that will get thrown into the mix as well. But we don't know which browser it is. We can still report, hey, we have high confidence this is a browser, which again adds context to the investigation. In the cases that we do know with high confidence that a specific client, then we can say so. So for example, if we have enough indicators that something is exactly Firefox, then let's call it exactly Firefox. And of course, as I mentioned before, we want to make sure that we're verifying data across the network rather than just saying it's one thing based off of a few fields or what have you, or just because it matched the mapping database. And that way we make sure that we're not reporting incorrect information based off of like corner cases. And we can use this network across, or the data across the network or across devices to, as I mentioned in the beginning, identify interesting clients for a device, identify interesting clients for across the network, or even interesting destinations for a specific application. As I mentioned too, we can move away from using a hash, which allows us to ask more specific questions relevant to TLS fingerprinting. And that allows us also to add new extensions and rules without breaking our old identifiers. So for example, some new extension comes out that is only used by Firefox or the NSS library, but not any other browsers, we can add that identifier to help us identify Firefox without breaking how we identify other browsers. So this is, this is basically what I have for everyone today. I hope that it was eye-opening information. I hope that we can agree to move forward away from a specific hash or what have you, And I hope that in the future, I might have a paper to share with you guys, which gets more into the weeds. And definitely, as we're developing this, hopefully we can, as an industry, decide, that this is a better option. I know.
Yeah, I've actually got another question for you real quick, Troy. Yeah. So one of the things that you were talking about, sort of in your proposal to shift away from, these hash-based, static methods, was the use of, sort of these mapping domains. And one of the things that just sort of popped up to me, I was thinking about, what if the attackers visit those, right? So what if the attackers visit those domains on purpose, fundamentally trying to trick everybody into thinking they're benign applications? Would that throw the method that you were describing off?
So, it's always possible for attackers to kind of pick up on what defenders are doing and then kind of use that against them in order to seem like benign traffic. I mean, I can already think of examples of what you're talking about. For example, when malware might reach out to google.com to do, a connection test or what have you, which is something you would not expect, or something you would normally expect to be benign, for example, or even using, Twitter or Gmail as C2 servers. Those are examples of those types of things. So I imagine that as this method is adopted, or if we're using it and attackers find out about it, they might try to do these kinds of things. Luckily for identifying or mapping applications based on domains, that's why I mentioned we need to make sure we verify the information across the network. If we see one corner case where some new TLS fingerprint that we've never seen before, some collection of different TLS fields reaching out to one of those mapping domains, but we don't see any other indication that it is that browser, or we don't see that same collection of TLS information on any other device on the network, in that case, I would definitely not want to map that to whatever application would normally be mapped to. Certainly, you could still include the information to say, hey, this would have mapped or what have you, but I definitely wouldn't say with high confidence that this is Chrome or Firefox or what have you.
Yeah, got it. It's never quite as simple as you'd like it to be, right?
Yeah, exactly. So yeah, I mean, you always have to, there's counterpoints from the attackers, and then you have to come up with your own thing too. But yeah, I mean, I guess if you thought about it in a sense, could someone then have the same TLS fingerprint or the same collection of cipher suites and then also visit that domain? Yeah, I mean, I guess you could argue that in that case, it would be difficult to separate the two, but certainly this method isn't a silver bullet to identify all bad things, right? So, and then I know, I mean, so I know we have time for some questions. Maybe if anybody had any questions from the audience. Certainly, if I don't get to any questions, feel free to reach out to me.
Okay, yeah, we do have some questions ready, so I'll jump in and get started.
Okay.
Someone asks, how would the new indicators be shared?
Yeah, so that's something that we're still talking about internally, because as I mentioned in the beginning, so something that JA3 does do is it gives you that hash that you can share. I think it's important that whatever we are sharing is accurate. And of course, as an industry, we probably disagree about the best way to share things. We think about all the different formats for indicators and things like that. So I'm not saying that we'll definitely come up with the best way to do that or what have you. I do want to sooner rather than later have some method of either making this method available to people so that they can run it on their own PCAPs or what have you, or even coming up with an example of how we can share this information, because just like verifying information across a network, of course, it's stronger if we verify it across an industry or a community. So it's certainly something that I want to focus on going forward.
All right, thank you. There's a follow-up question. He asks, what do the indicators look like, and how would they be implemented in SIMs or TIPs?
So it would essentially be a collection of TLS information. So if you can imagine it like a database, that's probably the easiest way to do it. So if you're recording this information in whatever database, and then you can query that information, and the fingerprints, again, not as straightforward as a hash, I suppose, but certainly more accurate in what I've seen. But it would be, even if it's as simple as here are the lists of extension values and things that we know, while also making sure that we are recording information like is grease present or is extension 21760 present or things like that. So again, I mean, obviously this requires more thought going forward on how we can make sure that it's compatible across the industry, but I would imagine that's how we've been doing things internally, and I imagine that's how it'll go forward in some form like that.
All right, thanks, Troy.
Mm-hmm.
Someone's referencing, they have a question, it looks like regarding slide 24. Wouldn't the domains used to map applications change over time?
Yeah, so they definitely can change over time. I did see that for specific domains that I was looking at for a lot of these applications, you can Google around and find forum posts from as far back as like 2006. So, I mean, I think 12 years is a pretty good shelf life for one of these mapping domains. And it certainly changes, it seems that they change less frequently than something like a JA3 fingerprint would with all of the updates to browsers and things like that. So, I mean, it is something to keep track of, but I think overall less to keep track of.
All right, thanks. Looks like we have a follow-up from the question before this last one. He says, will you be able to share these details that help identify library types like Fizz and others?
Yeah, I believe so. So that's what I was saying. I'm hoping to get, I know this presentation, like some of it was in the weeds and some of it was high level because it's only, about an hour long or so. But I don't see any reason why I can't get, more into the specifics. I mean, as I mentioned, if we don't get more into the specifics, then how do we share it? So yeah, I mean, that would be my hope. I mean, like I said, you can reach out to me anytime or just keep an eye on, LinkedIn or Twitter or something like that. And I'm sure that whenever any update comes out, I'll certainly share what I can.
All right, thanks. Mozilla and Cloudflare have recently announced that they support, I think it's ESNI. Will that affect the method you're proposing?
Definitely a possibility. So what ESNI is, so that's encrypted SNI or the encrypted server name extension. And so if you think about, mapping applications to domains, if we don't actually know what that domain is, then how can we map it? I did look into this a little bit, and the only application, well, I mean, first of all, so in order for ESNI to happen, both the client and the server have to support it, much like anything else. And right now, the only application or client that I'm aware of that supports it is Mozilla Firefox Beta, and the only destinations that support it, as far as I understand, are Cloudflare servers. And I actually, I followed their instructions on how to do it and wasn't able to get it to work right. So I think in that sense, it's still kind of in its infancy. And also in order to break the mapping, like the specific domains that are reached out to and shut down, things like that, would have to be using the ESNI, which means the developers of Firefox or Chrome or whatever application would have to make sure that those destination servers that they've been using for potentially more than a decade are now ESNI compatible. I'm not saying that's impossible, it's just something that would have to happen. It's also my hope that, at that time we'll have years of data to be able to identify browsers more accurately just using analytics without having to use the mapping database. So that's a possibility as well. So definitely something to keep an eye out for. Right now, I'm not too worried about it.
All right, thanks. I think you're trying to squeeze in one more.
Okay.
They ask, would slide 14 suggest that while there may be some variation of JA3 hashes for a single client, there may not be enough for us to bother coming up with a different mechanism for TLS fingerprinting?
Yeah, so that's a good question. So if you guys remember, basically I think you're talking about this slide right here. Essentially, so these are, two of them have the hash that's on the JA3 GitHub. Two of them don't, but they're the same hash. And if you look at the dates, you can see, 2017 for those two and 2018 for the others. So maybe these are just 2 different years. So I just picked the first 4 PCAPs that I found on malware traffic analysis. I probably could have found better examples to demonstrate my point. And I showed you guys the demos, right? which I think were probably better examples. So in the case of DRIDX, assuming that this is, representative of all DRIDX, then it could be the case that there's only a handful of hashes that we need to be aware of. However, because of the reasons that I mentioned before, with the differences in OSs and differences potentially in Word versions, if it's a downloader using macros, and malware in general, I think it's going to create just simply too many hashes. And, we mentioned possibly being able to circumvent detection methods, right? So, I mean, all you would have to do is change one value, or, go out to an IP address instead of a domain, or any of those things in order to change the hash. And so, it'd be very simple to change that.
All right, well, that's all the time we have for today. Thank you so much, Troy and Dave, for your great presentation, and to Awake Security. Yeah, great. And to Awake Security for sponsoring this webcast, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcast. Until next time, take care, and we hope to have you back again for the next SANS webcast.